Hello, you should be watching this video on Wednesday, and you may think, oh my goodness, she never even changes shirts. But this is actually the same day that I recorded all of the other stuff. So I recorded the last two videos the same day, and I had to move locations. So I'm doing this from my living room. So it's kind of a long story, but just go with it. So let's go ahead and do some math for 11.2. So you're going to need a few items before we get started. Please make sure that you have a writing utensil and paper, like notebook paper or whatever paper you can find. You can even add these sample problems to your notes from 11.1 if you wrote those out. And then you're going to need your textbook, calculator. So go ahead and gather those things. Pause the video if you need to. And then after we go over all the math problems that we're going to do today, please just take a quick picture with your phone and email that to sdixon, that's SDIXON, @evajax.com. So that'll give you credit for doing today's work. And then tomorrow you can do 11.2 practice on a Google form. So let's go ahead and dive in. Our first problem is going to be on page 304. At the bottom of the page. So take a moment. Again, you can pause the video if needed to find page 304, but we're going to go ahead and look at this problem. It's got a tree and an unfortunate house, which you'll see why it's unfortunate in a minute. So find page 304, and again, write these down as we go. Please participate. If you need additional time, pause the video, and that way you can get it all done without having to go way back and look for stuff. Okay, so the problem at the bottom of page 304, example problem 2, it says that a 22.0 kilogram tree limb is 13.3 meters above the ground. During a hurricane, and we know that can happen because we live in Florida, so sadly during a hurricane, the limb fell on the roof that is 6.0 meters above the ground. And so I'm going to go ahead, or I actually did already go ahead and write down what we're given, and I want you to do the same. Again, pause the video if you need more time. And I want to point out that the mass is in kilograms, which is appropriate, and the height is in meters, which is also appropriate. We want to stick with the units that correspond with the things that are in a joule. Kilogram, meter, second, newtons are fine because that's a variation of that as well. So we want those kinds of units. If something is in kilometers or grams or something like that, you know you're going to have to convert. Oh yeah, do you like my cover up? It's a cruise ship flyer. Anyone want to go on a cruise? I don't think so. Not right now. All right, so to solve this problem, we want the final kinetic energy. That you might think is tricky because we know that kinetic energy is 1/2 mv squared, but there is no mention of velocity in this problem. But I'm going to show you how we can solve it using the law of conservation of energy. And we're going to pretend like this is in a closed, isolated system. We're not losing any energy to sound or whatever, thermal energy. But we're going to, I don't need this anymore. We're going to use this idea that the initial kinetic plus potential energy is equal to the final kinetic plus potential energy. So go ahead and write this down. This equation is critical. And again, it's from the idea of the law of conservation of energy, and we're just saying that energy is completely conserved. Like we do not lose any energy. I'm going to see if I can brighten this up a little bit. Yeah, there we go. So we're not losing any energy at all. And then the other great thing about looking at it this way is one of these can zero out. Okay, we can say that one of these is totally zero. Which one is it? This one. Because at the beginning of the problem, when the limb is hanging in the tree, it does have potential energy, but it does not have kinetic energy because it is not moving. And so V1 would be equal to 0. So I'm just going to put an X through this. And then we're trying to solve, and I'm just going to circle it because we're solving for this. We're trying to solve for KF. And so I don't want to break that down, but I do need to break down these potential energies. And so it's been a while. But remember potential energy, which is PE, the formula for that. Oh, the light went crazy. Stop. Okay, maybe it'll stay right. PE equals mgh. Remember that one? And so we're going to break each one of these down. And so since this is the beginning one, it's going to be mgh1. And so I'm going to write that underneath it. And so instead of PEI, I'm going to do mgh1. And then I don't want to, I know KE equals 1/2 mv squared, but I don't want to do that because we're asked to solve for kinetic energy. So we need to leave it just as KEF. And then instead of PEF, what do you think we're going to put? MgH2. So, and if it were falling like straight on the ground, we could probably X that out because H would be 0, but it's not falling all the way to the ground. It's falling to that rooftop that's actually 6 meters above the ground. So we cannot zero out the PEF. All right, at this point, let's go ahead and solve for KEF because that's what we're supposed to find. So we're going to go ahead and, actually let me keep letting you look at this. We need to get this by itself. We need to get rid of this set right here. So this is being added. So to get it to the other side, we would subtract it. So I'm going to do minus MgH2 on both sides. I'm just going to make it negative for a second over here. Okay, so that's going to go. So we can say that KEF is equal to MgH1. I don't know why I tried to make that a small g. Minus MgH2. So you should come up with something like that. And then notice that both of these have mg in them. So let's go ahead and factor that out. So I'm going to say that the final energy is equal to mg times parentheses H1 minus H2. Oops, forgot my in parentheses. Sorry. And if you need more time, pause the video. Okay, at this point, can we plug in? Like, do we have everything? Yes, we do. So go ahead and plug it in. If you need more time than I'm taking, then you can definitely pause the video. Make sure you watch out for significant digits. We're going to use 9.8 meters per second squared for G, as always. Okay, and then it's kind of weird because we're used to doing H2 minus H1, but because the way that the math worked out for this, we're actually doing H1 minus H2. And so your problem should look like this. Again, pause the video if you need more time. And then go ahead and work that out in your calculator. Okay, so when I did it, before I rounded, I got 1573.88 joules before I rounded. And then how many significant digits? With these kind of problems, we're always going to be limited to just 2 because of that 9.8. Perhaps something might have 1, which nothing in here did. So let's round it to 2 significant digits, okay, which would be 1600 joules. So that was A. Very good. Okay, and then of course there's a B too. So in B, it says, what is the limb speed when it reaches the roof? So we're trying to solve for, I put V squared, for V2. So, or VF, whichever one you want to say. So VF or V2. And so we know the kinetic energy, the final kinetic energy. So here's where we would break it down into 1/2 mv squared. And so we're going to say that KEF is equal to 1/2 mvf or V2 squared. Same thing, VF, V2, whatever. It's fine. And then we just need to solve for V. And so we had one like this, I think on 11.1. And so this is kind of actually a review and a redundancy of that. But go ahead and get rid of everything but your VF. So this 1/2 we can get rid of by multiplying both sides by 2. So we're going to go ahead and do 2 on both sides like that. And then let's get rid of the m by dividing. So it'll look like that. Again, feel free to pause your video at any time. And then I'm going to clean it up to be VF2 is equal to 2KEF over M. And then the last thing we need to do is get rid of the fact that this is being squared. The opposite of squaring something is to take the square root. So we're going to take the square root of both sides. So we end up with VF is equal to the square root of 2KEF M over M. Now, this is one of those situations where if you had these problems back to back and you got the wrong kinetic energy, guess what's going to happen? You're going to get the wrong velocity. So I could do correct for data and stuff like that on this problem. It just makes it a little bit harder sometimes to grade, but keep in mind that you definitely want to try to get this one right so that that one's right. Also, I want to point out that, like, say you still had this number in your calculator, it's actually a little bit more accurate if you retain that and use that for this problem. If you use the rounded up version, I'm going to kind of have to keep that in mind when I grade things like this, because people could be rounding a little bit differently depending on what number they actually use for KEF. So I'll keep that in mind as I'm grading as well. Okay, when I did it, I just used the 1600. So I did it was equal to the square root of 2 times 1600 joules over M, which is 22.0 kilograms. So before I rounded, I got 12.06 meters per second. And then we're rounding to two significant digits again. So 12 meters per second it is. And I'm not used to doing math in pen. I'm just doing it in pen so it shows up better for you guys. Seems weird though. Okay, so that's the first one. Okay, it was long. It was actually 2 problems. You know, we love to do that to you guys. Sorry about that. The next problem, we're going to flip over in your book to, wait for it. Okay, page 308. So let's take a look at page 308. Example 3. And I have this one written down, so I'm just gonna I hope this works instead of writing it all out again. But let's read the example problem again. We're on page 308, example problem 3, and we're talking about cars this time. That's what it should look like. And it says, in an accident on a slippery road, a compact car with a mass of 1150 kilograms moving at 15.0 meters per second smashes into the rear end of a car with a mass of 1575 kilograms moving at 5.0 meters per second in the same direction. Okay, and it looks like they stick together. That's actually kind of important. A, what is the final velocity of the wrecked cars locked together? Okay, they do say that they're locked together. That's good. Good to know. And so if you look at it, when you write this stuff down, we've got both of the masses and we have both of the velocities. And then I just labeled the cars A and B. You can label them 1 and 2 or X and Y or whatever you want. Just as long as you keep them straight yourself, you're good. So the first question is A. It says, what is the final velocity if the wrecked cars lock together? Okay, so we're going to find VF. And you can see my notes. We have to use the concept of momentum. So we're going back again, like you see how we keep on building on the knowledge that we already had. So remember the simple formula for momentum. Momentum is represented by a P, and that's equal to mass times velocity. And so we're going to use the concept of that and the concept of conservation of momentum to solve this problem. So we're going to say that since they stick together, and you need to, I'm using my cruise ship thing, but it's upside down. Would it make you feel better if I showed you the boat side? Sure. There we go. All right, so we're going to say the initial momentum of car A plus the initial momentum of car B is equal to the final momentum. There's no A and B over here because they stick together and they're treated now as one object. So when we do that, I think we did something similar to this back when we did the momentum chapter, but we're going to break it down into the momentum of A initially would be the mass of car A plus its initial velocity, times its initial velocity. And then the momentum initially for car B would break down to the mass of car B times the initial velocity of car B. Okay, and then over here, since they stick together, they have the same velocity. I just put VF, that says VF, actually, now can you read it better? That says VF, but then I had to add their masses together. And so pause the video a little bit more if you need to write that down. All right, once we do that, we can move on because we want to solve for VF. And so this is what it looks like when you solve for VF. Again, pause the video if you need more time to write all that down. And then you're ready to plug in numbers. And so this is kind of labor intensive, but I'm sorry, I'm trying to hold this still. There we go. Okay, and then when you solve the problem, okay, you get something that rounds to 9.2 meters per second. Okay, and again, pause the video if you need more time. Okay, and then if by directionally, it'll be in the same direction that the cars were initially moving, because the one car rear-ended the other car and they kind of combined into one mass and continued in the same direction. So you can just put in the original direction when you're giving the direction for momentum because it's a vector quantity. All right, so with that, the second question, we're still in that same sample problem. B says, how much is the kinetic energy decreased in the collision? And so we want to know how much the kinetic energy decreases. So we need to find out delta KE here. Wait. So we're on B now. We're finding delta KE, which is going to be the final kinetic energy minus the initial. And each of those can break down into 1/2 mv squared, but we're going to make it irrespective of like whether it's the beginning or the end, whatever. So when we break that down, let me go ahead and cover it up like this. Okay, when you break it down, it looks like this. So you can pause the video if you need more time. And then when you plug in all of your numbers, I don't want to show that yet. Oh goodness. Okay. Here we go. There we go. Just like pause it or whatever, and then you can finish writing it all down. Okay, so these aren't super hard. They're just labor intensive and you have to think things through. If you just really think about what's happening, what kind of energy, what's the little formula for that, you can work these out. It's all good. Okay, one more sample and it is not in the book. So I'm going to flash this problem up. You're gonna have to pause the video and write it down. Okay, so this is an interesting problem because it says that you drop a coin of unknown mass. Like, we don't really even care how much the mass is, which is kind of crazy. But if you have a coin of unknown mass and you drop it from a height of 2.62 meters above the ground, how fast will it be moving just before it hits the ground? And we can actually figure this out pretty easily using that lovely conservation of energy equation. So go ahead and copy that down. This comes in handy so much, so often. And then 2 of these can zero out. So that's going to make this problem a lot shorter. So think about it. If you're holding a coin out and you're about to drop it, and then you drop it, which 2 of these can zero out? Okay, think about that. And I'm going to go ahead and X out the correct ones. Let's see if you're right. X them out. Make your decisions. All right, were you correct? The initial kinetic energy zeroes out because when you're just holding the coin out, it's not moving. So there's no initial velocity. So that one zeroes out. And then just before it hits the ground, the height will be 0 essentially. So that one zeroes out. And so all we have to do is worry about these. And so since I'm trying to figure out how fast it will be moving, that's velocity, I need to go ahead and break these down into their respective formulas. So PE, potential energy equals mgh. So for the PE initial, I'm going to do mg initial height times the initial height. I'm just going to put that right underneath it because PE equals mgh. And then KE equals 1/2 mv squared. So for this specific one, I'm going to put 1/2 mvf squared. Do not forget the squared part. Okay, now, since I want to solve for velocity, I just need to start moving things around till I get VF by itself. And so let's get rid of this fraction right away. So let's multiply everything by 2, like that. And then something really cool happens. Let's get rid of mass. Watch what happens when you get rid of mass, because you need to divide by mass on both sides. And it cancels out not only on one side, but the other side. That's how come we can not care about how much mass it has. And so let's clean this up, because we now really have VF by itself. I'm just going to clean it up and switch the sides on you. So it is VF squared, so don't forget the squared part. So VF squared is equal to 2 times HI. Oh, I forgot the G. Hang on. The G is in there still. Okay, so let me redo that. So VF squared is equal to 2G HI. H sub I, by the way. Okay, so there we go. And then we're going, that was scribbled out, this one right here. And then we need to get rid of the square part by taking the square root. So take the square root of both sides. So you get VF is equal to 2GHI, or the initial height. And we are ready to plug in. So that's going to be equal to 2 times 9.8 meters per second squared. And then the initial height is 2.62 meters. So run that in your calculator. Oh, you know what? We got to square root it. Forgot my square root. So that's what you should get. Square root that thing. And then before you round, again, pause if you need more time, because I really want you to follow through and do it on your own calculator. But when you do this calculation, it's going to be 7.1660 meters per second before you round. And of course, we'll be rounding to 2 significant digits. So it rounds to 7.2 meters per second. I'll hold this up too, because it's confusing with that other stuff down there. All right. So this concludes all of the sample problems that we're going to do. You'll see some like it on the 11.2 practice tomorrow. Today, all you need to do is go and click on the link to the form. Say, yes, I watched the video. I'll probably ask you some random question, answer that as well. And be prepared to do 11.2 practice tomorrow. Thanks and have a great day.